So let's take a look at the chain rule. So let's say we have z, which equals to some multivariable function in terms of x and y. We have an x equation in terms of t, and then we also have a y equation in terms of t. And so given this information, how could we find dz dt? Well, you have to use the chain rule. And so the formula for this type of chain rule is going to be dz dt equals the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. And so there are two ways you can use a chain rule, and so this is going to be the first way. So this is going to be called case number one. So once again, case number one is where you have a multivariable function, z equals f of x comma y. You have an x equation just in terms of t, and you have a y equation just in terms of t. So for this next set of problems, we have to use the chain rule to find either dz dt or dw dt. So for number one, z is going to equal x squared y plus xy squared. The x equation is going to be equal to 2 plus t to the fourth, and the y is equal to 1 minus t cubed. So once again, using the formula given up top here, let's go ahead and first find the partial derivative of z with respect to x. So we're basically taking the partial derivative of this equation with respect to x. So x is going to be the variable, y is going to be the constant. So the partial derivative of z with respect to x is going to be equal to, so if y is the constant, derivative of x squared is 2x, so we get 2xy plus, and so the partial derivative of xy squared, if y squared is a constant, the derivative is simply just y squared. And so now if we were to find dx dt, all we have to do is derive the x equation. Since there's only one variable, we don't need to take the partial derivative, we only need to take the regular derivative. So dx dt is going to be equal to the derivative of 2 plus t to the fourth, which is simply just 4t cubed. So now the partial derivative of z with respect to y. So now we derive this treating y as the variable and x as the constant. So the derivative of x squared y is simply just x squared plus, now the derivative of xy squared, derivative of y squared is 2y, so we have 2xy. Now the partial, or not the partial, dy dt, as shown in the last bit of the formula here, dy dt is going to be the derivative of the y equation with respect to t. And so the derivative of 1 minus t cubed is simply just negative 3t squared. And so now if we plug everything into the formula here, once again dz dt, or the derivative of z with respect to t, is going to be equal to the partial derivative of z with respect to x, which we found to be 2xy plus y squared, times dx dt, which we found to be 4t cubed, plus the partial derivative of z with respect to y, which we found to be x squared plus 2xy, times dy dt, which is negative 3t squared. So if I rearrange the terms for the final answer, we get dz dt equals 4t cubed times 2xy plus y squared. That's a negative here, so we can put minus 3t squared times x squared plus 2xy. So now for number two, we have z equals sine of x times cosine of y. The x equation is equal to pi times t, and the y equation is equal to the square root of t. So let's first go ahead and find the partial derivative of z with respect to x. So in that case, x is going to be treated as the variable, y is going to be the constant. So derivative of sine of x is cosine x, so we get cosine x times cosine y. And so dx dt, we're just going to take a look at the x equation and then derive it with respect to t. So the derivative of pi times t is simply just pi. Now the partial derivative of z with respect to y, so this time y is the variable, x is going to be the constant. So the derivative of cosine y is negative sine y. So we have negative sine x times sine y. And then derivative of y with respect to t. Let's go ahead and look at the y equation. So the derivative of square root of t is simply just 1 over the 2 times the square root of t. So once again, for the formula, dz dt, or the derivative of z with respect to t, is going to be equal to the partial derivative of z with respect to x, which is cosine x times cosine y, times dx dt, which is pi, now plus partial derivative of z with respect to y, which is negative sine x times sine of y, times dy dt, which is 1 over 2 square root of t. So now to simplify, we'll get dz dt equals pi times cosine x times cosine y, minus, I can bring the negative out front, sine of x times sine of y over 2 times the square root of t. So now for number 3, we have w equals x times e raised to the power of y over z. X is going to be equal to t squared, y is equal to 1 minus t, and z equals 1 plus 2t. So notice that we don't just have 2 input variables, x and y, now we have 3, so all x, y, and z. So remember the original formula where dz dt equals the partial derivative of x, or the partial derivative of z with respect to x, times dx dt, plus the partial derivative of z with respect to y, times dy dt. But now our equation is not z equals, our equation is w equals. So in this case we have to find dw dt. So the derivative of w with respect to t is going to be equal to, now we're going to replace all z's with w's, so the partial derivative of w with respect to x times dx dt, plus the partial derivative of w with respect to y times dy dt. And now since we have an extra z variable here, we can simply just add plus the partial derivative of w with respect to z times dz dt. And that's going to be the formula for this specific problem. So first let's go ahead and find the partial derivative of w with respect to x. So we're just going to look at the partial derivative of this equation, but in this case x is the variable, everything else is treated as a constant. So derivative of x e to the y over z is simply just e to the y over z. Now dx dt, deriving the x equation, derivative of t squared is simply just 2t. So now let's find the partial derivative of w with respect to y. So in this case, y is going to be the variable, everything else is a constant. So remember, the derivative of e to the u, some function u, is going to be equal to e to the u times u prime. So this is going to be equal to x e to the y over z times the derivative of the inside function. So if y is the variable, the derivative of y over z is simply 1 over z. So then we get x e to the y over z over z. And so now dy dt is going to be equal to the derivative of 1 minus t, which is simply just negative 1. So now let's find the partial derivative of w with respect to z. So this time z is going to be the variable, everything else is a constant. So once again, derivative is going to be x e to the inside function, y over z, times the derivative of the inside function. So now if z is the variable, I can rewrite y over z as y times z to the negative first. Since z is going to be the variable, I need to use the power rule on just z, and y is a constant. So we get, bring the power down, so negative y times z, and then subtract the power by 1 to the negative second. So we get negative y over z squared. So when I multiply by negative y over z squared, I can simplify, and then we'll get negative x y e to the y over z over z squared. So now dz dt, deriving the z equation with respect to t, derivative of 1 plus 2t is simply just 2. So now I can plug in everything into the formula. So once again, dw dt, this time we're finding the derivative of w with respect to t, using the chain rule, is going to be equal to the partial derivative of w with respect to x, which we found to be e raised to the power of y over z, times dx dt, which is 2t, plus the partial derivative of w with respect to y, which is x times e raised to the power of y over z, times dy dt, which is negative 1, and then plus the partial derivative of w with respect to z, which is negative x times y times e to the y over z over z squared times dz dt, which we found to be 2. So if I simplify this, we'll get 2t e to the y over z, now minus x times e to the y over z, and then we have, I can bring that negative out front, negative 2xy e to the y over z over z squared. So if I want to, I can also factor out the e over e to the y over z. Then we'll get 2t minus x minus 2xy over z squared. So now the next set of problems are going to be about the second case of the chain rule, or when to use the chain rule. So this time the z equation is going to be the same. So z is going to be equal to some multivariable function in terms of x and y. But this time we're given an x equation in terms of not just t, but s and t. So x in terms of s and t, and the y equation is also going to be in terms of s and t. So this time we're going to find the partial derivative of z with respect to s, and you're also going to find the partial derivative of z with respect to t using the chain rule. And so the formula for the partial derivative of z with respect to s is going to be equal to the partial derivative of z with respect to x times the partial derivative of x with respect to s plus the partial derivative of z with respect to y times the partial derivative of y with respect to s. And so the formula for the partial derivative of z with respect to t this time is going to be equal to the partial derivative of z with respect to x times the partial derivative of x with respect to t this time. Since we're deriving z, we're taking the partial derivative of z with respect to t plus the partial derivative of z with respect to y times the partial derivative of y with respect to t. So notice both of these are going to be the same on both equations. The only thing that's different is depending on what we derive with respect to. So if we derive with respect to s, all of these are going to have s's. If we derive with respect to t, all of these are going to have t's. So for these problems, we have to use a chain rule to find the partial derivative of z with respect to s and the partial derivative of z with respect to t. So for number 1, we have z equals x squared plus x times y plus y squared. X is equal to s plus t, and y is equal to s times t. So let's go ahead and start by finding the partial derivative of z with respect to s. So let's go ahead and first find the partial derivative of z with respect to x. So the partial derivative of z with respect to x. Now x is going to be the variable. Everything else is a constant. So derivative of x squared is 2x. Derivative of x times y is a positive y. And the derivative of y squared is 0. And so let's go ahead and find the partial derivative of x with respect to s now. So in this case, the partial derivative of x with respect to s is going to be equal to, now s is going to be the variable, t is a constant. So the derivative of s plus t is simply just 1. So now finding partial derivative of z over the partial derivative of y, that is going to be equal to, well, this time y is the variable, x is the constant. So derivative of x squared is 0. Derivative of x times y is just simply x. And then derivative of y squared is plus 2y. And then let's find the derivative, or the partial derivative of y with respect to s. So in this case, we have s times t. If s is the variable, t is the constant, then the derivative of s times t is just t. So using the formula here, the partial derivative of z with respect to s is going to be equal to the partial derivative of z with respect to x, which is 2x plus y, times partial derivative of x with respect to s, which is 1, plus partial derivative of z with respect to y, which is x plus 2y, times the partial derivative of y with respect to s, which is t. So if we simplify, we'll get 2x plus y, and then plus, I'll just leave the t outside, so t times x plus 2y. So now let's go ahead and find the derivative, or the partial derivative of z with respect to t. So notice both formulas have partial derivative of z with respect to x and partial derivative of z with respect to y in both of them. So we've already found both of those, so this step is much easier, because all we need to find now is the partial derivative of x with respect to t and the partial derivative of y with respect to t. So the partial derivative of x with respect to t, if t is the variable, s is the constant, then the derivative is simply just 1. And then for partial derivative of y with respect to t, if t is the variable, once again, s is the constant, then the derivative will be s. So now, once again, using the formula, partial derivative of z with respect to t is going to be equal to partial derivative of z with respect to x, so 2x plus y, times partial derivative of x with respect to t, which is 1, plus partial derivative of z with respect to y, which is x plus 2y, times partial derivative of y with respect to t, which is s. So if we simplify, we'll get 2x plus y plus, and I can just leave the s outside, s times x plus 2y. So for number 2, z equals arctangent of 2x plus y. X is going to equal s squared times t, and y equals s times the natural log of t. So let's go ahead and first find the partial derivative of z with respect to x. So looking at the function here, z equals arctangent of 2x plus y. If we are deriving with respect to x, and x is the variable, y is the constant, remember the derivative of arctangent or inverse tangent of some function u, of some inside function, is going to be equal to u prime over 1 plus u squared. So take the derivative of the inside function and then add or divide it by 1 plus u squared. So if we take the derivative of 2x plus y, and we're deriving with respect to x, derivative of 2x is 2 and the derivative of y is 0, so we get 2 plus 0 up top, over 1 plus the entire inside function squared, so 2x plus y squared. So now let's go ahead and find the partial derivative of x with respect to s. So in this case, we can look at the x equation here. If s is the variable that we derive, then t will be treated as a constant. So then the derivative will simply just be 2 times s times t, so 2st. So now let's find the partial derivative of z with respect to y. So in this case, y will be the variable, x is the constant. So derivative of arctangent of 2x plus y, we're going to take the derivative of the inside function. So derivative of 2x is 0, derivative of y is 1, over 1 plus the entire inside function squared, so 2x plus y squared. So now the partial derivative of y with respect to s is going to be equal to, now s is the variable, t is a constant, so the derivative is simply just natural log of t. And so if I plug everything into the formula now, the partial derivative of z with respect to s is going to be equal to the partial derivative of z with respect to x, which we found to be 2 over 1 plus 2x plus y squared, times partial derivative of x with respect to s, which is 2 times s times t, so 2st, plus the partial derivative of z with respect to y, which is 1 over 1 plus 2x plus y squared, times the partial derivative of y with respect to s, which is the natural log of t. So now if I simplify, 2 times 2st is 4st, over 1 plus 2x plus y squared, and we have plus 1 times natural log of t, over 1 plus 2x plus y squared. Notice the common denominators are the same, so we can go ahead and combine the fractions together. So 4st plus the natural log of t over 1 plus 2x plus y squared. So now let's go ahead and find the partial derivative of z with respect to t. So notice in the formula we need partial derivative of z with respect to x and with respect to y. We already have those two. So now all we need to find is the partial derivative of x with respect to t. So in that case, if t is the variable, s is the constant, the derivative is simply just s squared. And the partial derivative of y with respect to t, once again, t is the variable, s is the constant. So we have s times the derivative of natural log of t, which is just 1 over t. So we get s over t. So now plugging into the formula, the partial derivative of z with respect to t is going to be equal to the partial derivative of z with respect to x times partial derivative of x with respect to t. If I go ahead and multiply those two, we'll get 2s squared over 1 plus 2x plus y squared, and then plus partial derivative of z with respect to y times partial derivative of y with respect to t. So then if I multiply those two, I'll just leave s over t on the numerator. So we get s over t over 1 plus, same common denominator here, 2x plus y squared. And so to simplify and go ahead and combine the fractions with the same common denominator, so the partial derivative of z with respect to t is going to be equal to 2s squared plus s over t over 1 plus 2x plus y squared. So the next set of questions are going to be about implicit differentiation and how you can use a chain rule to do implicit differentiation. So let's say you have a function with two variables, so you have f of x comma y. Well, the formula you can use to find y prime or dy dx is simply going to be equal to negative f sub x over f sub y. F sub x, once again, is equal to the partial derivative of f with respect to x, and f sub y is once again the partial derivative of the function with respect to y. So once again, this is the general formula to use to find dy dx. So let's go ahead and find dy dx. So for number one, we have the square root of x times y equals 1 plus x squared y. So the very first step we have to take is to bring everything to one side of the equation. So we have to say 0 equals, let's go ahead and subtract the square root. So 1 plus x squared times y minus the square root of x times y. And then we can go ahead and replace the 0 and set the equation equal to f of x comma y. So if I go ahead and erase that, we got this equation or this function equals f of x comma y. So now what we can do is go ahead and find dy dx. So once again, dy dx is going to be equal to negative f sub x over f sub y. So once again, how can we find f sub x? Well, once again, f sub x is the partial derivative of the function with respect to x. So x is the variable, everything else is a constant. So derivative of 1 is 0. Derivative of x squared is 2x, so we get 2xy. And then minus, now I can change this or rewrite it as x times y to the 1/2 power. And so the derivative, or the partial derivative of xy to the 1/2 is going to be 1/2 times xy to the negative 1/2 times the derivative of the inside function. And so if we're deriving with respect to x is the variable, so the derivative is simply just y. So if I simplify this, we'll get 2xy minus y over 2 times x times y to the 1/2. So now let's find the partial derivative of f with respect to y, or f sub y. So this time y is going to be the variable, everything else is a constant. So derivative of 1 is 0, plus the derivative of x squared y, which is just going to be x squared. And then minus, now we have the derivative of xy to the 1/2. So same process, we're going to derive and we get 1/2 times xy to the negative 1/2 times the derivative of x times y. So if y is the variable, derivative is going to be x. And so to simplify, we will get x squared minus x over 2 times xy to the 1/2. So for both of these, f sub x and f sub y, I'm going to go ahead and find common denominators. So if I were to simplify or condense into one single fraction here, I'm going to go ahead and multiply 2xy by the common denominator. So 2xy times 2 times xy to the 1/2 will give me 4xy times xy to the 1/2 over 2 times xy to the 1/2 minus 4 over the same common denominator. And so to combine into one single fraction, then I can put it as 4x times y times xy to the 1/2, or the square root of xy, minus 4 over the same denominator, 2 times xy to the 1/2. Now the same process with f sub y, I'm going to go ahead and find the common denominator. So I'll multiply x squared by 2xy to the 1/2. So we get 2x squared times xy to the 1/2 over 2 times xy to the 1/2 minus x over the same denominator. So when I combine the fractions, we will get 2x squared xy to the 1/2 minus x over the same denominator. So now dy dx is equal to negative f sub x over f sub y. So if we go ahead and divide these two, if I multiply by the reciprocal, those two will cancel, and so we're left with, remember, don't forget the negative, so we have negative 4. Now xy times xy to the 1/2 can be rewritten as xy to the 3/2 minus y over 2x squared times xy to the 1/2 with the square root of xy minus x. Now if you want to, you can also distribute the negative to the numerator or denominator, so let's go ahead and just distribute it to the denominator. So then we'll get 4 times xy to the 3/2 minus y over x minus 2x squared. I'll just rewrite xy to the 1/2 as the square root of xy. So that is going to be equal to dy dx or y prime. Now the next form of implicit differentiation is when you have a function with 3 variables this time, so x, y, and z. And so in this case you need to find 2 things. You need to find the partial derivative of z with respect to x, and you need to find the partial derivative of z with respect to y. So the formula for the partial derivative of z with respect to x is going to be negative f sub x over f sub z, and the formula for the partial derivative of z with respect to y is going to be equal to the negative f sub y over f sub z. So let's go ahead and find partial derivative of z with respect to x and the partial derivative of z with respect to y. So number 1, we have x squared plus y squared plus z squared equals 3xyz. So similar to the previous problem, we need to get everything to one side of the equation. So I'm going to go ahead and subtract over the 3xyz. So that's going to be equal to 0. And then now I can get rid of that and then set it equal to the multivariable function, so f of x comma y comma z, since we have 3 separate input variables here. So once again, the formula for the partial derivative of z with respect to x is going to be equal to negative f sub x over f sub z. So let's go ahead and find f sub x first. So f sub x is going to be equal to, now x is going to be a constant, everything else, or x is going to be the variable, everything else is a constant. So derivative of x squared is 2x, derivative of y squared is 0, z squared is 0, and the derivative of negative 3xyz, if once again x is the variable, so the derivative is 3yz. And so now for f sub z, z is going to be the variable, everything else is a constant. So derivative of x squared is 0, derivative of y squared is 0, derivative of z squared is 2z, and derivative of negative 3xyz is simply just negative 3xy. So now if we go ahead and use the formula, so partial derivative of z with respect to x is going to be equal to negative f sub x, which is 2x minus 3yz, over f sub z, which is 2z minus 3xy. So I can go ahead and distribute the negative if I want. I'll just go ahead and do that to the numerator. So we'll get positive 3yz minus 2x over 2z minus 3xy. So that is going to be the partial derivative of z with respect to x. So now let's find the partial derivative of z with respect to y. Now the formula once again is going to be negative f sub y over f sub z. Notice we've already found f sub z, so we can keep that. And so let's find f sub y. So now y is going to be treated as the variable, everything else is a constant, so derivative of x squared is 0, the derivative of y squared is 2y, derivative of z squared is 0, and the derivative of negative 3xyz is going to be negative 3xz. So once again, using the formula, the partial derivative of z with respect to y is going to be equal to negative f sub y, which is 2y minus 3xz, over 2z minus 3xy. So if I go ahead and distribute the negative to the numerator, the partial derivative of z with respect to y, the final answer is going to be 3xz minus 2y over 2z minus 3xy.